Yesterday, we went over scalars and vectors, just review of Science 10. We did a little bit of V equals D over T stuff. Okay, want to do another little bit of D over T stuff that you still would have done in Science 10, but it's a little bit more involved. Okay, and focus on how we solve something that's vector versus how we solve something that's scalar. Okay, and then kind of a two-part problem like what's on the board here. Okay, so just quick review. Yesterday, we decided that the scalar quantities we're dealing with are distance and speed and time. All right, the vector quantities we're dealing with are displacement, velocity, and acceleration, which we haven't gone over yet. Okay, so here's the thing that I want to introduce or remind you of from Science 10. Okay, this formula here, but I want the thin marker, only ever gets written like this. Sometimes it'll have AVE beside it, which stands for average. Okay? But what it really means is this. This is never written beside it, but it's what it means. Okay? Average velocity is the total displacement divided by the total time. Speed is the same. Okay? Average speed is total distance divided by total time. Okay? This is important if we have a situation where the situation we're dealing with has two or more parts. Okay? So let me give you an example. Let's say I drive to Edmonton, and for the first 290 kilometers, I am able to just put the cruise on and go at 110. Okay? Nothing stops me, slows me down. I go 110 for 290 kilometers. Then I get to the south end of Edmonton, and for the last 10 kilometers of the trip, I have to slow to 50 kilometers per hour. Okay? Is my average velocity halfway between 110 and 50 for that whole trip? Or is it way closer to 110? Okay? It's way closer to 110, right? I went 110 for 99% of that trip. Okay? I only had to slow down for the last 10 kilometers of the trip. It doesn't affect my average very much. Okay? And the reason I bring that up is because of the way you've been taught to calculate averages in your life. Okay? And that would be, I add all the things I have together, and then I divide by the number of things that I have, and that gives me the average. Okay? Which works if everything you're adding together represents an equal part of the whole thing. Okay? So if I'm calculating a class average, every one of you represents an equal part of the whole class. So I add all your scores together, divide by 32. Okay? But I can't do that for a situation like driving to Edmonton where I travel 290 kilometers at 110, but the last 10 kilometers I have to slow down. Okay? I wouldn't add those two numbers together and divide by 2, then my average velocity would be like 77. There's no way. Okay? Does that sort of make sense? So what we do is we use this idea to weight the average in favor of whatever part of the trip counts for the most part of the trip. Okay? So if I was to do it that way, I would probably get a number that would be more along the lines of an average velocity of like 108. Okay, it would be really close to 110 because that, in the end, represents what I did for most of the trip. Everyone kind of following me there? Okay. So, in a situation like this question, this is exactly what we just talked about. Okay? We've got a bus that travels 11 kilometers at 21 meters per second and then slows for 1 kilometer traveling at only 4.2 meters per second. Okay? I want you to calculate for me the average speed of the bus over the entire trip. Okay, so I'll give you a little tip here on kind of how to get this started. The first tip is, you're not going to need this formula because we're calculating speed and not velocity. All right, here is what I would do. As part of writing down my givens, I would break this up into the different parts of the trip. Okay, there are 2 parts to the trip, and since I know I'm going to be looking for the average velocity or average speed, I know I'm going to need these 2 things. So I'll make another column that I will call the totals. Okay, I know I'm going to need the total distance and the total time. Okay, so here's my suggestion. Write down the givens for part 1 and for part 2. See what you need, okay, and calculate what you don't already have. Right? I'm going to point out one other thing. Your distances are in kilometers. Your speeds are in meters per second. Do your units need to match before you can do any math? Yeah. Easier to convert kilometers to meters or meters per second to kilometers per second? Kilometers to meters, way easier. What do you multiply by? 1,000, okay? And guys, by the way, metric conversions, got to be able to do those on the fly in this course, okay? Kilo always means 1,000. That's the beauty of the metric system. All right, I'll give you a few minutes on that. So if we're looking at our givens here, it tells us that in part 1, it travels a distance of 11,000 meters, and it does that at a speed of 21 meters per second. And in part 2, it tells us that the distance traveled is only 1,000 meters, and that the speed is smaller at 4.2 meters per second. Okay, can I get my total distance traveled right now? All right, I know the distance for both parts. My total distance traveled is?
1,200 meters?
12,000 meters, yeah. Okay, so I've got that. But I don't have the times yet. Can I get them for both parts? It's the same calculation twice, right? I just have to take V equals D over T and solve for T. So I would multiply both sides by T and then divide both sides by V. So T will equal D over V. All right, so T is going to be D divided by V, 11,000 divided by 21. Sorry guys, my calculator got shut off here. And for some reason it doesn't start up as quick as yours. Okay, so we'll take our 11,000 divided by 21. Okay, so 523.8 with some other decimals seconds. Should I keep all those decimal places? I absolutely 100% should. Okay, for significant digits' sake, I do not round anything off until I'm at my final answer. Okay, keep all of the decimals all the way through until you get to the end. I'm not going to write them all because they're stored in my calculator, okay, but I'm going to keep them there. So 523 seconds is what I'll write here. Okay, I need to do the same calculation here for part 2, so that's going to be 1,000 divided by 4.2. All right, and that's 238 seconds. I'll keep all the decimals in my calculator. All right, now can I get the total time? Okay, just add those two together. Okay, so 761.9 seconds. Okay, again, I'll keep all the decimals in my calculator. Am I good now to calculate the average speed over the whole trip? I've got total distance and total time. Okay, so now it's just V equals D over T, 12,000 meters, divided by 761.9 seconds. Okay, we'll keep all of our decimals there, so 12,000 divided by that number. Okay, we only have 2 significant digits in that question. Okay, so our answer here has to be rounded to 2 significant digits, and that means 16 meters per second. Okay, I know I haven't talked about significant digits yet, so if that sounds like Greek to you right now, that's okay. We'll cover it here this week. All right, everybody follow what we did there? Okay, is any one part of that very difficult? It's just v equals d over t. But sometimes the pattern, the route to getting from beginning to end can be a little tricky. Okay, so in this one, everything we dealt with was scalar. Okay? Direction didn't matter here. Would this question be different if instead of this being scalar, this was north and this was south? Would it change then? Okay, what would I do with the 11,000 and the 1,000 instead?
Subtract.
I would subtract them, because now one is north and the other is south. Okay, they're in opposite directions. Okay? Or I would add them and I'd make the south negative or something along those lines. Okay, that's really all that would be different to solve a question like that. Okay, so I'm going to make up one here real quick that has a vector part to it. Okay, we'll write that one down as an example and then give it a try. I'll give you a few minutes to get ahead of me here. Basically the same idea as the last one. It's just for the first part, vectors matter. So for this one here, same as we did before. Anytime you see a question that's got clearly two different parts to it, okay, you want to separate your givens out into those two parts, or three parts, or however many it has. Okay, and then get your totals, right? And we know we're going to need totals because they want average velocity, which is total displacement, sorry. Okay, over total time, so I'll need that. Okay, and I'll also need total distance because I'm going to need it for average speed later. So those are the three things I've got to get. Okay, what I have is the displacement in part one, 150 meters up, okay, and the velocity in part one, 8.3 meters per second up. All right, so, and then in part two, I've got the displacement, 80 meters down, okay, and the time, 14.2 seconds. All right, so when looking at my givens, I can see that I have a change in direction going on. Right? Up and down are opposites, so I have to apply positive to one of them and negative to the other, so it works out mathematically. So what I often do is if I have a question like that, I just go up equals positive, okay, down equals negative. Right? And then I keep it straight in my head after that. Okay, can I get the total displacement and the total distance right now? Right? I've got the numbers for both part one and part two. Okay, if we go 150 meters up and then 80 meters down, what's our total displacement?
70 meters up.
70 meters up. Okay, 150 plus negative 80 or minus 80, okay, is going to be 70 meters up. What's my total distance? Does distance care whether it went up or down? Distance is just how far the elevator went, right? 230 meters. I just add those, right? 80 plus 150 is 230 meters. No vector on that. That's just how far the elevator went. Okay, I don't have the total time because right now I don't have the time for part one. Is that something I can calculate with what I have? It is. So time equals d over v. 150 divided by 8.3. Okay, so that's going to be just over 18 seconds. I'm going to add those two numbers together. All right, so I've got 32.07 seconds. I'll keep all the decimals in my calculator. All right, am I at the point now where I can calculate the two things the question asked for? Yeah, I think so. Okay, I've got the total distance, total time. Okay, so my average velocity, okay, total displacement, 70 meters up, divided by the 32.07 seconds. Okay, so 70 divided by that number there. Okay, so my average velocity to two significant digits, because that's what I've got here, okay, is 2.2 meters per second up. Yeah. Okay, our displacement was up, so our velocity is up. They're always going to have the same direction. Okay, to get my average speed, total distance divided by total time. Now it's 230 divided by the 32.07. All right, and so for that, we're looking at 7.2 meters per second.
Your total time is wrong. You added 14, not 14.2.
Did I?
Yeah.
You are absolutely right. Okay, let's check that again. Thank you. Sometimes I get ahead of myself and get going too fast. Okay, so we got to change that, and that. Okay. Good catch. Okay, so 18.07, this number here, plus 14.2. Okay, so 32.27. It's probably just going to change the decimal, but still valid. Okay, 70 divided by the correct time now. Okay. Oh, it's still 2.2. Okay, I was lucky. Okay, and then this one may still be the same as well. 230 divided by, but we should always have the right numbers. Oh, no, that one went down. So that one's only 7.1. Okay, good catch. Okay, any questions on how that worked besides Coderre can't add? That happens from time to time. All right, so that's kind of the Science 10 review stuff, okay? What we're going to look at next here is some vector stuff, okay? How do we represent vectors? How do we put them together? Okay, how do we kind of show their components? Okay, all of that kind of stuff, and that's going to lead us into what we're going to be doing for probably the next couple of weeks, okay? Is all this vector component stuff, okay? All right. Now, the vector stuff that you've been doing in Science 10, what we did yesterday and today, okay, those kind of vectors are what we call collinear vectors, or one-dimensional vectors, because they only go forward or backward, north or south, up or down, okay? They're always perfectly in line with each other, okay? Those are collinear vectors, okay? We're going to look at those just as kind of how we understand how we represent vectors, the conventions going around that, and then we're going to move on to how do I add vectors that are perpendicular, which is something you haven't done, right? So, an object goes, 100 meters forward and then turns and goes 50 meters right. Okay, so that would be a right angle. Okay, they would be perpendicular vectors, and we would have to find their displacement, okay, along the shortest route between the beginning and the end. Okay, right angle triangle. What kind of things do we use with right angle triangles?
Pythagorean theorem.
Use Pythagorean theorem, okay, and we use trigonometry to get the angles. All right, so that's where all of that stuff is going to come into play. All right, so we got to understand what collinear vectors are. We just talked about that. Learn that all types of vectors are added by placing them tail to head. We call it the tail to head method. It just means that you draw one vector and then you draw the next vector coming off the end of that one. Okay, kind of like you're storyboarding something. First this happened and then this happened and then that happened, and you just draw them one after the other. Okay. All vector quantities obviously have magnitude and direction, something we already talked about, okay? And then all vector quantities, regardless of what it is, displacement, velocity, acceleration, force, they're all added the same way. The only thing that's different is what units you put on your final answer, okay? But the mechanics of what we're going to learn applies to all vector quantities. All right, so the conventions, excuse me, for drawing and representing vector quantities. Okay, we represent vector quantities with arrows. Right? Now, a vector quantity has both magnitude and direction. So there's two qualities of the arrow that we use to represent those things. Right? The first is we point the arrow or draw the arrow in the direction that vector is supposed to be going. Right? So in the case of the vector you see here in this picture, that vector is directed 30 degrees north of east. Okay, so I've drawn that arrow as though it is pointing 30 degrees, okay, north of east. Okay, why didn't I just say northeast? What's the point of saying it north of east?
Because it wasn't straight there? Like turning straight there?
No, it's still straight. It's still pointing that way. But northeast represents this whole sector of a compass. Agreed? That whole sector would be considered northeast. But within that sector, there are two 30 degrees northeasts. One of them is 30 degrees east of north, and one of them is this one, 30 degrees north of east. It depends where you measure the angle from. Those are definitely two different directions, right? I mean, there's 60 degrees between those. Okay, we wouldn't want to, pick the wrong one. You would probably not end up where you intended. Okay, so the way we say this, or why we say north of east, is we say, okay, here's our arc, our angle arc that we always draw. Whatever main direction it touches, that's the one you're of. Okay, this went north of east.
Good to know. Pretty sure it's just a 30-degree difference between the two.
What did I say?
60.
Well, that was wrong. Yeah. I get going on stuff. Get things in my head. Okay. I think you guys pay attention. See, you're catching all my mistakes. I like that, actually. I don't mind. If I make a mistake, you guys point it out, because that means you guys are paying attention. My other classes, I could do something completely wrong, nobody will say anything. Okay? Definitely point it out if I make mistakes. I'm getting old, and not as sharp as I once was. Okay, so this is 30 degrees north of east, because I measured it from east and went north of there. This one is east from or of north. Everyone follow how we say that? Okay, why we say it that way? Okay. It's something you'll get used to. It's probably not something you've done before, but it is something you'll get used to. All right, so we draw the arrow pointing whatever direction we're given. Okay? The other part of this is we use the length of the arrow to represent the magnitude. So a 2-kilometer vector is this long. A 3-kilometer vector would look like that. It would be longer. Okay? We use the length of the arrow to represent the magnitude of the vector we're given. Now, please do not figure out a scale and measure everything. Okay? Don't bring a ruler or a protractor or anything like that. That is a total waste of time. Okay? As long as you're reasonably accurate with your drawings, you will be fine. Okay? I haven't measured an angle or a line in probably longer than you've been alive. okay? And my vector diagrams still turn out okay, okay? Because scale's a little bit important, but there's no need for exacting measurements, okay? All right, so we draw the arrow pointing in the direction of the vector or along the vector we're given, and the length of the arrow, okay, is representative of the magnitude. So a 4-kilometer vector is twice as long as that one, okay? At least as best you can. By the way, you also need to know your compass directions in case you don't know them.
If north of east is 30 degrees east of north and vice versa, is northeast 45?
Yes, that would be the only vector that would be truly northeast, okay? But we would still say 45, yeah. And you could give the complementary angle. If I said it's 30 degrees north of east, you could also say it's 60 degrees east of north. That's the same direction, right? Those two lines are pointing the same way. That's, I think, what I was thinking when I said the 60. Okay, okay. Questions on the conventions for drawing? Okay, length represents magnitude, and we point the arrow in the direction the vector is given. So, a simple collinear vector question could look something like this. The question tells us that we have this car, and this car is going to drive 275 meters due east, and then it's going to go another 125 meters due east. So I draw those two vectors, but I draw them tail to head. Okay, so this is the tail, this is the head. All right, so I draw the first one here. This would be 275 meters, and we typically do right beside them what the magnitude is. And this one is 125. They both point due east, okay, and I just draw them one after the other. I put the tail of the second on the head of the first, and it always goes that way. Even if you've got 5 vectors, right, the tail of the fourth would go on the head of the third, and so on. So once I've drawn those, they would add up to this red line. Okay? The red line is referred to as the resultant. Depending on what you're adding together, the resultant can represent lots of things. In this case, it represents the total displacement because I added 2 displacement vectors together. If I added 2 velocity vectors together, it would represent the average velocity. If they were accelerations, then it would be average acceleration. If it was force, it would be net force. The resultant is just whatever the addition of those 2 things is. Everybody all right with that idea? Okay. In a collinear situation, we probably don't bother to draw it. Probably not necessary. In something else where the vectors are going different ways, then we would draw the result. Questions on that? That's pretty straightforward, right? You guys have done ones like that. You've just never seen the drawing before. So this just finishes it up. We call this the tail to head method, and all vector addition is done in that manner, regardless of what vector quantities you are adding. So what if I had a situation where a person walked 10 meters south and then went 5 meters west? What would that look like? That's my 10 meter south vector. What would I do with the 5 meter west vector?
Have a dot at the bottom of that arrow and turn it left.
Yeah. That might be a little short. Okay, it should be half of the 10. It's about half. and it points to the west. I draw them tail to head. Doesn't matter what they're doing, they get drawn tail to head. This one happened first, that one happened second. You go chronologically along with your diagram. Questions there? All right, so let's look at that as an example here. So same car that we were dealing with before. This time it goes 275 meters due east, then turns and goes due north for 125 meters. So according to the way we draw diagrams and vectors is we would draw our 275 and write the magnitude beside it. And then we would draw the 125, and we use green just so we tell them apart here, 275. No, sorry, 125, not 275. So the red line is still my resultant. In this case, the resultant represents my total what?
Displacement?
This would be my total displacement. These were both displacement vectors. 275 meters due east, 125 meters due north. Those are two displacement vectors. So I drew them tail to head. This here represents my total displacement. It is the car's change in position. This is the car's initial position. This is the car's final position. Just like that thing we did yesterday with the walk to Walmart, right? You had to go a whole bunch of different directions. In the end, your displacement was the straight line between start and finish. And it always will be. So if that represents my total displacement, which is a vector quantity, I need both its magnitude and its direction. How do I get its magnitude?
Pythagorean?
I would use Pythagorean theorem. I know two sides of this right angle triangle, 275 and 125, so Pythagorean theorem should get me C, right? A squared plus B squared equals C squared. Believe that comes out to 302, if memory serves, but we just saw that I'm not as sharp as I used to be, so we might as well actually do it. $302 meters. That's the magnitude of my total displacement. This would be my vector, or the direction of that displacement. How would I get that? Do I know all three sides of the triangle now?
Yeah.
Can I use trigonometry? Okay. And I can use any trig function I want at this point because I know all three sides. I could use sine, cos, or tan because I know all three sides. My suggestion, and it's not just because I actually have a favorite trig function and it happens to be tan, okay? But I would also use tan because it uses the two numbers I was given in the question and not the one I calculated, just in case I mess up. And I'm using two numbers I know are actually right. So, to get this angle, all right, I would go tan of theta equals 125, the opposite side, divided by 275, the adjacent side. I'm looking for theta, so that's inverse tan of 125 over 275. I think it comes out to 24, if I recall. So it comes out to 24.4 degrees. What direction should I put on that? North of east, exactly. My angle arc, as I have it drawn, is touching due east. The line is north of due east, so north of east. Right. You could also say the complementary angle, and it would be east of north, and that would be fine. Okay, so our final answer here, 3 significant digits. The total displacement is 302 meters at 24.4 degrees north of east. probably the first time you've used all of those skills that you already have in a way like this. But we're not asking you to do anything you haven't done in other classes like Math 10C, where you do your trigonometry, or Math 20, where you do trigonometry as well, I believe. So nothing new there, okay? Know your sine, cosine, tan, your SOHCAHTOA, and no Pythagorean theorem. Okay. Does that make sense to everybody? How we do that? So really what we're doing anytime we're adding vectors is we got to find out how far does it go horizontally and how far does it go vertically. Because there'll be times where we'll have more than two vectors and we'll have to figure out, okay, this one went this far in a positive or in a north direction, this one went this far in a south direction, put those together, and this other vector went east and then east again, so I add them together. Okay, that's kind of where we'll be headed. Anybody need that up there anymore? All right, here's an easy one for you. Okay, I want you to do this question about the most boring town in the entire world. These are collinear vectors, right? They all go forward. They all have the same direction here. So if I'm drawing the vector diagram for this one, I would first draw a 10-meter vector. Okay. I would draw a 5-meter vector, it's about half as long, and then a 25-meter vector. Okay. I didn't measure those, but they're at least approximately to scale. Like I said, it doesn't have to be exact. As long as it's representative, you're fine. Since they're all forward, can I just add them all together? Okay, so my total displacement then, if I was actually going to bother to draw a resultant, which I wouldn't for collinear vectors, it would look like that. And it would be 40 meters forward. Any questions on that one? All right, I would like you to try question number 7. The diagram is helpful, but it is actually a bit more of an algebra trick in the end. But the idea here is that it's going to illustrate how important or helpful a diagram can be, even when we're talking about collinear vectors. Okay, so we're just told that this car drives north 500 kilometers, and then it has 3 sequential parts of the trip in the opposite direction, and its final position is 50 kilometers north of where it started. You need to figure out the 3 sequential displacements back. And spoiler alert, it is a bit of an algebra trick. Okay? But the diagram can help you out. So I'll give you a few minutes on that one. I would never ask you one like this on a test because it is more of an algebra trick. The point of this question is to illustrate why a diagram can be useful. So here's what we know. We know the car goes 500 kilometers north. And then it tells us that there are 3 sequential trips or parts of a trip back, and that each one is 50 kilometers longer than the one before it. The problem is we don't know how long the first one is. So it's all well and good to tell me part 2 is 50 kilometers longer than part 1, and 100 kilometers, and part 3 is 100 kilometers longer, but that doesn't help me figure out what part 1 is. What can help me with that is a vector diagram. I know the first part back is n. I don't know how long it is. I'm just going to say it's n. The part after that is 50 kilometers longer than that. I probably didn't do this to scale very well. And then there's the last part, which I didn't do a very good job of. It's n, it's 50 kilometers longer than this one, so it's n plus 100, and then I'll fudge my diagram. Okay, and this is 50 kilometers. So those 3 sections that I don't know add up to what? 450. Okay, that's where the diagram is helpful. I know the overall displacement is 50. I know it went 500 kilometers north. So I know that these things I don't know add up to 450. So I can say 450 equals n plus 50 plus n plus 100. Fair to say? Everyone okay with what I wrote there? Does that make sense logically? Right. The diagram is what helped me figure that part of it out. So if I can bring the numbers I actually know over to here, okay, by subtracting them, what I'll be left with is that 300 equals n plus n plus n, or 3n. Can I figure out what n is now? Yeah. So divide this by 3, n equals 100. So this is 100, this is 150, this is 200, and I'm pretty sure that adds up to 450. Okay? It's an algebra trick, okay, for sure, but you can't even get to the algebra unless you've got a diagram there that can help you kind of lay it out. All right, so just trying to illustrate the importance of drawing those tail to head diagrams, even for something collinear like this, to help us figure out what those things could be. Okay, write this one down. This is a really good vector problem. Okay, draw the diagram and then see if you can figure out this person's total displacement. So what the person does first is it says they walk 0.8 kilometers south. All right, so I'm going to go 0.8 kilometers, that's south. Then they go 1.2 kilometers east. Okay, drew it tail to head, right? I put it on the head of the first one, because first they did this, and then they did this, and then after that, they went 0.3 kilometers back north again. Okay, I didn't measure these, they're just approximately to scale, and it'll get the job done. Where would I draw a line now that would represent the total displacement of this person?
The start of the 0.8 kilometers to the end of 0.3 kilometers?
Right, because this is my initial position, and this is my final position. And displacement is your change in position with both magnitude and direction. So this line right here would be the total displacement of the camper. How am I going to get that line? Can I make a triangle with it?
Don't you just take the south side and then minus the north side?
Yeah, to get the vertical component or the north-south component, absolutely. Okay, I need to know how far south or north did they go? Well, they went 0.8 kilometers south and then went back 0.3 kilometers north. That means, at least with my math, that they ended up 0.5 kilometers south of where they started. But they also ended up east of where they started. How far east?
1.2 kilometers.
1.2 kilometers. Is it okay for me to say that that would be the east and south components of that vector? In the end, that's what they did. Along a straight line, there's some change in position from their beginning position, but they are definitely 1.2 kilometers east and 0.5 kilometers south of where they started. Now that I know those sides, can I get the total displacement? Okay, I'm going to give you a couple more minutes to get it if you don't have it already. Since I know the two sides of my displacement's triangle, right, I know how far east it goes and how far south it goes, then I can use Pythagorean theorem to figure out at least the magnitude, how far that displacement is. All I have to do is take the 1.2 squared and add it to 0.5 squared. Pretty sure that comes out to 1.3. So the magnitude of my displacement is 1.3 kilometers. But displacement is a vector quantity, which means it needs magnitude and direction. The way I drew that triangle, my angle arc touches east. If you drew the triangle this way, that's also fine. You're just going to get the complementary angle, and it'll be the opposite of mine. Okay? So, when I do this calculation, 0.5 is the opposite side, 1.2 is the adjacent side. So theta will be tan to the minus 1 of 0.5 over 1.2. Okay, so 23 degrees. And for me, that is south of east. But if you drew this triangle, you're finding that angle, which is totally valid. If you do, this will be flipped, and you'll get instead 67 degrees east of south. Those two are the same direction. They're just measured from a different reference line. Everybody all right with that? And in the end, again, the only thing that was new for you here was drawing the diagram tail to head. You know how to do Pythagorean theorem, and you know how to do trigonometry. You're just applying it. You're making it useful. Instead of being, you know, a purely mathematical thing that's done for no purpose other than coming up with the right answer, now you get to use it for something good. That's the joy of physics. Okay? Instead of just doing math for the sake of mathing, now we make it do good stuff. Okay? Math is a tool. Anyone who tells you otherwise. All right, questions on how that works? So here's where we're headed. In the next couple of days, we'll start working on ones that look like this. Okay, so now I've got two vectors, but they're both angled. But I drew them tail to head. Where would I draw a line on that diagram that represents the total displacement of that object? Is this my initial position?
Yes.
Is this my final position?
Yep.
Is displacement your change in position? That line is my total displacement. Now, is this starting to make you like, oh my God, there's so many lines that are all overlapping? That's okay. It often makes people feel that way at first. Okay. At this point, people who've had my class before are like, Coder, I thought you hated triangles. Okay. And I do when they're used for algebra. I don't mind them when they're used for this. This is what they're for. Okay. Now, this isn't actually any different than this. All I have to do is figure out how far east this thing went and how far south it went. Same as I did in the last one. But I do that by doing trigonometry on the two vectors I was given to start out with. Since I know the hypotenuse of this green triangle, could I figure out what this side and this side are? Right? I have a side and an angle. I can figure out everything else about a triangle as long as I have those two things. Right? So I could figure out how far east this line goes and how far south this line goes. And I can do the same thing with this triangle. Using the hypotenuse in this angle, I could figure out how far north it goes and how far east it goes. Okay? And then I would put the x's together. That would tell me how far east it goes. I'd put the y's together, and that would tell me how far north or south it goes. And then I'd have the two sides of my purple triangle. Okay? It's always gonna be the same set of steps. All the changes is gonna be, I might have to do more work to get all of the sides that I want, okay? Here's the good news. Right now, that's probably like drinking from a fire hose, and that's okay, all right? But it's always gonna be the same pattern. No matter what I give you, you'll always do the same steps. Sometimes you might have to do more of those steps, depending on how many vectors there are, but they'll always be the same steps. So once you learn the pattern, these are actually pretty straightforward. Okay? Even though right now you're probably looking at that and going, how do I drop this class by tomorrow? Okay, you don't have to worry about that. There's a way to do this, and once you've done a few of them, you'll get the pattern. Okay? All right, so that's where we're headed. We're obviously not there yet. Okay. We already did that one. Okay, I want you to write this one down and give it a try. Okay, we'll finish off class with this one. So just to make sure everybody's kind of started this one correctly, I'm just going to draw the diagram here so you can see it. Our first vector was 20 meters south. Our second vector was 5 meters north. And our last vector was 8.5 meters west. Okay, so our total displacement would be that line right there. Okay. So to finish this one off, I have to find out our two sides, or what we will refer to going forward as our X, or horizontal component, and our Y, or vertical component. In this case, those are compass directions, west and south. The only time the band goes east or west is right here. So they end up 8.5 meters west of where they started. But they go 20 meters south and then 5 north. So green Y is going to be how much? 15. 15 meters south. Now that I know those two sides, I got to do Pythagorean theorem. 15 squared plus 8.5 squared. Squared plus 8.5 squared. All right, so we're looking at 17.2 meters, and then we got to get the angle, so that's trig. So theta will be tan to the minus 1. The way I drew it, 15 over 8.5. All right, we're looking at 60.5. We only have 2 significant digits, so we're looking at 17 meters at 60 degrees south of west. Okay. If you had 30 degrees west of south, that's also fine. Just depends on which way you drew the triangle. All right, we're going to continue working on that tomorrow. Guys, good work today.